Okay, take a moment please and sketch this function, and please note that it is a graph of f, not f prime or f double prime. In this video we're going to be looking at the second derivative and what it tells us about f. We talked about how the first derivative tells us a lot about f. It tells us where f is increasing or decreasing, or where we have a relative min or max. The second derivative is also useful for telling us some information about f. So please make sure that you have marked off these three key points. Okay? So our second derivative deals with concavity. Okay? And when I say concavity, I'm referring to concave up or concave down. The first derivative dealt with whether or not a function was increasing or decreasing. The second derivative deals with if a function is concave up or down. So by concave up, we are referring to a portion of the graph where it is bent upward. So this section right here that I just pointed to, we say is concave up. If a function is concave up, the second derivative is going to be a positive number, so it's going to be greater than 0. Alright. Now this region right in here where it's bent downward, we say that is concave down. And if it's concave down, the second derivative is negative or less than 0. So let's back up for a moment and look at this point, this special point where the concavity changed. Okay, this is called an inflection point. And an inflection point, by definition, is a point where the concavity changes. Okay, and where the second derivative is equal to 0. So at this point here, at my inflection point, the second derivative, f double prime of x, is equal to 0. So it's simply an inflection point, and by definition, it's where the concavity is changing. So you can see that it's going from positive to negative. Okay, so the second derivative changes sign. Okay, so let's look at this key point. This is another inflection point, IP for inflection point. You can see our function is going from concave down to a region now where it is concave up. Okay, and we said if it's concave up, our second derivative is going to be positive, so greater than 0. So we can see that this function is bent upward for a while, and then we move into another inflection point, where the concavity changes. So in other words, the second derivative is going from either negative to positive or positive to negative. So on this portion of the graph, it's now bent downward. So this is concave down, meaning the second derivative is less than 0. Okay? So if a function is concave down, it is bent downward, it has a negative second derivative. If a function is concave up, it has a positive second derivative, and it looks like that. Alright, so this is a little visual to help you remember that this is concave down, and this face is concave up. Okay, let's look at one example of a function where we will analyze it using both the first and the second derivative. So here is our function. Let's go with f of x is equal to x cubed minus 3x squared minus 2. Alright, so our goal is to graph this function, let's say, without the use of a calculator, and we want to use calculus principles to analyze it. So over here we will actually produce our sketch eventually. Alright, so let's go to our first derivative. 3x squared minus 6x. Let's use our first derivative test, which recall is to set it equal to 0 and solve and look for what we called critical points. So I can factor out a GCF there. If I solve, I get x equals 0, x equals 2. Now remember, these are known as critical points. They're points where the derivative is either equal to 0 or undefined. Okay, in this case the derivative is never undefined, so these are the only values for our critical points. Let's make a quick sign diagram for this. So we're going to label it f prime. So we have x equals 0, x equals 2. The first derivative was 0 at each of those points. I'm going to put a 0 there above each of these. To the left of 0, let's test something like -1. And I'm going to test it in the factored form of my derivative. If I plug in -1, I have a negative times a negative. That gives me a positive. Let's plug in 1. That gives me a positive times a negative. So that's a negative. And let's plug in 500. I have a positive times a positive. So that's definitely positive. Okay? So what this tells me, recall, let's jot this down here. This plus means that f is increasing. The minus means that f is decreasing. And then again over here, increasing. So if I am going to be increasing and then decreasing, alright, at this point right here, I have a relative max. Now if I were to plug 0 into my original function, alright, I get 0, -2. So those are the coordinates for my relative max. And likewise, over here at 2, the function is decreasing and then it's going to increase. So that means I have a relative min. If I were to throw 2 into my original function back up here, alright, where I see an x, I'll save you some time. You're going to get -6. Alright, we should know how to plug in 2 and get -6. So these are some key points. Alright, so let's start our graph here. So we know 0, -2 is going to be on our graph. And we know that 2, -6 is going to be on our graph. Okay. So we have a relative max and we have a relative min. Alright. So that's just telling us where the function is increasing, decreasing, where we have these min and max values. So now let's go to the second derivative. So the second derivative, of course, is just the derivative of the derivative. So the derivative of, if I go back to my second derivative, it would be 6x minus 6. Well, this is now known as the second derivative test. It's the same concept. We're going to set it equal to 0. We're going to solve. Alright. Now we get x equals 1. Now most of the time this is going to end up being an inflection point because we can see it's a point where the second derivative equals 0. But it's only going to truly be an inflection point if the second derivative changes sign, meaning there's a change in concavity. So we're going to make another sign diagram using the same principles as before. So I know that when x is 1, the second derivative is 0. So I'm going to mark a 0 above that. Plug into your second derivative equation. Alright, something to the left of 1. That's going to give us a negative, and then something to the right of 1, something greater than 1. That's a positive. Now understand what these signs tell us. The negative here on the second derivative tells us that f is concave down. Remember, these sign diagrams are describing f. Okay? So the second derivative here, if it's positive, it tells us f is concave up. Well, because there is a change in sign on the second derivative sign diagram, it means we have a change in concavity, which means at x equals 1, we have an inflection point. Now if I were to plug 1 back into this original function, you're going to get -4. So 1, -4 is my inflection point. Okay? So to put these pieces all together, alright, I'm going to just label this IP for inflection point. This was a relative max and this was a relative min. Alright, so let's grab a different color here. Alright, we have to use these two sign diagrams to help us put these pieces together and draw this function. So first, let's start to the left of x equals 0, alright, to the left of our max point. So for x values smaller than 0, I need to draw something that is increasing and at the same time concave down. So we're looking at x values less than 0 to start. Alright, so I need something that is increasing and concave down. So increasing from left to right and concave down. Hopefully you're thinking something like this. That is increasing and is bent downward. Okay? Now let's focus between 0 and 1 for x values. Between 0 and 1 up here, f is going to have to decrease, and between 0 and 1 here, we're still talking concave down. So decreasing and concave down. Hopefully you're thinking it looks like that. Okay? It's decreasing and bent downward. Well, now at x equals 1 we have our inflection point. So now my concavity has to change. So to this point my function has been concave down. Now it needs to change and become concave up. Well, when x equals 1 up here in my first derivative sign diagram, f has to be decreasing still. So hopefully you're thinking that. So now it's decreasing and it's bent upward. Okay, it's concave up. And beyond this point of 2, f is going to start to increase and we're looking to be concave up. Okay, for the rest of the way. So increasing and concave up would look like that. So I'll throw an arrow on the other side. Okay, this is a sketch of our function f. Okay, and you could of course put that into the calculator to check it. Alright, adios.